All right, so we've just got 3 more class periods. Today we're going to finish up comparing means in the really, I think, usual case where the variances are not equal. And we'll start talking about linear regression, the last chapter, chapter 12 for us. Next Tuesday, only talk about linear regression. And then next Thursday, talk still some more about linear regression as well as review for the final exam. Final exam will be a mixture of problem types from the first 3 exams with changed numbers, changed functions, that kind of thing. Maybe changed wording, especially like on a true-false question or so. And then some new problems related to chapters. What chapters are they? Chapters, well, 9, 10, and 11. So, all right, so let's first focus on a comparing means problem when the variances are assumed to be unequal, or what to do when you don't bother to check whether the variances are equal or not. And even if they are equal, or really close to equal, maybe you could still use this approach anyway, okay? So as a kind of a default, I would typically use this approach of just going with the unequal variances approach. So the situation is a new coal liquefaction process is being studied. It's claimed that it results in a higher yield of distillate synthetic fuel. So I guess that's some sort of gas fuel. These observations are obtained in the number of kilograms that are obtained with a new process and the old process. Oh, and I was going to enter these in my calculator ahead of time, but I forgot to. So we're going to set up null and alternative hypotheses needed to support the stated claim that we think maybe the new one is better. Did they say that? It's being studied. Okay. It is claimed that it results in a higher yield. So sorry that I forgot to, I did plug these numbers, some numbers in a different problem in my calculator ahead of time, but I forgot to plug these numbers in. So bear with me as I plug these numbers in my stat mode. I've already got list 1 and list 2 taken care of, so let's go move on to list 3. So the new numbers will be in list 3, 16.4, 12.8, 15.4. Make sure you pay attention here and tell me if I make a mistake typing these numbers in. 17, 17.7, 12.2, 18.7, 15.9, 14.7, 19.1, 11.3, 14.1, and 16.5. 13 numbers, 16. I'm going to go backwards through them and double check. 16.5, 14.1. So far, so good. And then list 4, I'll do the old numbers. 11.1, 10.5, 10.9, 10.1, 12.8, 13.2, 12.6, 12.1, 14.5, 15.6, 14.2, 15.3, and 14.2. And once again, we're in a situation where the sample sizes happen to be the same. And again, they don't have to be the same. They don't have to be the same, but they are in this case. Let me double check the second list again. Going backwards through it here. Okay. So again, what is the claim? The claim is the new process is going to result in more kilograms produced. Okay, you can, by the way, this is not a bad idea. You can glance over the new numbers and the old numbers, and you can look at those and say, yeah, it does seem like the new numbers probably are going to have a higher mean. And if they were a lot higher, right, if those numbers were in the 20s, you would say, in all likelihood, I would bet money that I'm going to reject the null hypothesis here. Now, they're not in the 20s, they're in the teens. So it's not so clear whether you're going to reject the null or not. But The alternative hypothesis then would be that mu1 is bigger than mu2. It would be a right-tailed test. We are talking once again about comparing means here, not proportions or variances now. And the null hypothesis, use the equal one, that mu1 equals mu2. Excuse me. And again, you could think of these in terms of differences of means. Like this if you wanted to. And that does justify the test statistic that we use when you think of it that way. It's interesting. I mean, with means and proportions, when we're comparing population means or population proportions, we focus on the differences. Remember from last time, when we focus on comparing population variances, we focus on the ratio, one divided by the other. There's two different ways you can compare two numbers. You can either subtract them or you can divide them to tell which one is bigger than the other. Reason we choose this for means and proportions is because it makes the math easier as far as the statistics go, the theory. And with the variances, the reason we can choose the ratio is it makes the math easier as well. We can use that F distribution, whereas if we were subtracting variances, evidently it's not so clear what distribution to use. So you can write it either way. We're more used to writing it like the one on the left, but you could write it like the one on the right. Part B says, since putting the new process into production is very expensive, a type 1 error is costly. So type 1 error is rejecting the null when the null is true, which means you think the new process is better when it's really not. You're going to pour money into this new process, but it's really not better. A type 1 error is costly. To compensate, you can, why did they say to compensate for this? A type 1 error is very costly, so we should actually reduce alpha. Once again, we're in a situation where, like, you know, I typed this 15 years ago. When we're looking at this problem, why would they not use a smaller alpha when they say a type 1 error is very costly? Oh, it's because I typed it wrong. That should be alpha equals 0.01, not 0.1. Okay, so when a type 1 error is very costly, either time, money, or people's lives, you don't want to make a type 1 error, you should make alpha smaller. Okay. We could compute a p-value. We could also compute a rejection region, or we could think about it both ways. Of course, you don't have to think about it both ways when you do the test. You could think about it one way or the other. But maybe for instructional purposes, we should think about it both ways. However, we should use the degrees of freedom, the appropriate degrees of freedom here. And what is the appropriate degrees of freedom? Well, it's given by the Smith-Satterthwaite approximation, that crazy formula that I mentioned last time. When you're in the situation where the variances are assumed to be unequal, that was always an unpleasant situation more than 30 years ago, because people had used the Smith-Satterthwaite formula to approximate the best degrees of freedom to use. Instead of n1 plus n2 minus 2, they did this. Yeah. Okay. Well, am I going to use that formula? I don't really want to. So let's use technology instead. What happens if we do, well, if we do a statistical test with calculator? What are we doing? We're doing a 2-sample t-test. We're using a t-distribution. Remember, we started off with hypothesis testing using z. When we assumed the population variance was known, we were focused on one mean. Then we moved on to using t when we were focused on one mean, but the population variance was unknown, which is pretty much all the time. So the first situation really, you should probably never use. Then we moved on to talking about proportions, and we went back to Z. We had an interlude with variances and talked about the F distribution, but now we're back to comparing means, and we go back to using T. So we need appropriate degrees of freedom. We need a two-sample t-test here. I've got my data rather than my summary statistics. If I click the stats one, then I've got to plug in the sample means, x1 bar and x2 bar, the sample standard deviations, sx1 and sx2, and the sample sizes, n1 and n2. But if I got the data plugged in to my list, they were list 3 and list 4, then I don't need to compute those sample statistics, though if I asked you to, you should be able to do that and write them down. It's a right-tailed test. Are we pooling? No, we're not. We're not doing a pooled variance. We're not computing SP squared, that pooled variance, because we're assuming the variances are unequal. It was the previous section where we did the pooling. So you could decide to assume the variances are equal and do the pooling. Maybe before I do this test, I should go back out here. Let's not do the test yet. Maybe we should just look at the sample standard deviations and see if they are relatively close together or not. I mean, I'm not going to change my final approach in the end anyway, but if I do two variable stats, I won't get an error because the sample sizes are the same. List 3 and list 4. There we go. SX, which is for L list 3, that's the new, it's about 2.43. SY is about 1.84. Far enough apart that this feels comfortable saying the variances are unequal. And especially if you square them, they're going to get further apart. The variances are going to be further apart than the standard deviations are. Okay, go back to test. So we're not pooling. Calculate the p-value. Will it calculate anything else? I think it does tell you the degrees of freedom. The t statistic is about 3.16. The p-value is small, about 0.002. We're going to reject the null. And the degrees of freedom, 22.3697. How can a degrees of freedom not be a whole number? Well, the Smith-Satterthwaite formula definitely can give you a non-whole number. But wait a minute, what does that mean about how would you, like, which t distribution would you use? You could round down. Rounding down always plays it safe to 22 degrees of freedom. That's a conservative approach if you use a lower degrees of freedom. And then you could use the table, or you could use t-ind on the calculator. It's telling you summary statistics as well here. And do notice 22 degrees of freedom is different, even though n1 and n2 are the same. It's different than n1 plus n2 minus 2. n1 plus n2 minus 2 would be 24. If we assume the variances were equal, and we did that degrees of freedom, we get 24 degrees of freedom. The Smith-Satterthwaite is giving us something smaller. It's being a little bit more conservative, you might say. And we could also round down to 22. So with the technology, which you can do for your homework, we're essentially using the p-value approach. It's good to say what t is as well. With technology, I mean, you can write down these statistics as well, but well, okay, you should at least write down the formula for t, just to remind yourself what it is. It's x1 bar minus x2 bar minus 0, the null value of the difference, but minus 0 doesn't need to be written, divided by essentially a standard deviation or an approximation of a standard deviation of a sampling distribution. I wrote this down before, square root of S1 squared over N1 plus S2 squared over N2. I won't take the time to do it, but it might be worth you checking that when you plug in the numbers there, you know, you could, it's a little bit of a pain, but you could do it in about a minute or two. You should get this number about 3.160, say to 3 decimal places, this T statistic. The degrees of freedom from the calculator, also technology, is about 22.4, which you could round down to 22, say. And even if it were 22.6, I'd still recommend rounding down to 22 to play it conservative. The p-value is about 0.002, less than 0.01, which is the alpha. We're going to reject the null. So we are going to say the new process is better. Let's compare what would happen if we use this T statistic with 22 degrees of freedom with the table. Degrees of freedom, I'm looking at the T table, 22 degrees of freedom. I'm looking across that line. My T statistic again was 3.16. Where is 3.16 on this line? It's between these two numbers. So the CDF value is between these two numbers, and therefore 1 minus those two numbers is what your p-value is between 0.001 and 0.005. 0.002 is between 0.001 and 0.005. Yeah, rounding the degrees of freedom down plays it safer. If for some reason we decided we wanted to use anything in smaller degrees of freedom, not that I'm recommending that, but just because we felt like playing it safer. For example, we decided to use, well, let's be extreme here and say 1 degree of freedom. 3.16 is between these two numbers, and your p-value would be between 0.05 and 0.1, bigger, making it harder to reject the null. Now that is playing it safer. You're not rejecting the null. You're not going to make a type 1 error. However, it is less accurate. You can fairly accurately say in this context that the p-value is about this. Playing it safer means making it harder on yourself to reject the null, making it harder to make a type 1 error. Questions? Question? Mm-hmm. Yep. Whenever the p-value is less than alpha, that's when you reject the null if you are approaching the problem based on a given level of significance alpha. Yep. Because intuitively, the p-value being small means you have observed something unlikely to occur when the null is true, something rare, something unlikely to occur by chance when the null is true. Therefore, we say the null, we think the null is false. We reject it. Small p-values are strong evidence against the null. If we were trying to do this in terms of a avoid a p-value but focus on a rejection region, we could figure it out in terms of the T statistic by using inv T. If alpha is 0.01, the area to the left is 0.99. These are CDF values for that area. Degrees of freedom, if we use 22, this is going to give us the boundary of the rejection region in terms of T. It's going to be something smaller than 3.16. About 2.5. So any T statistic bigger than this, 2.51, would lead to rejection in this context at the 1% level of significance. So as far as finishing the problem goes, you are rejecting the null. That alpha is supposed to be 0.01. Therefore, as far as recommending whether the new process should be used, because you're rejecting the null, you say, yes, use the new process. It does seem to be more efficient, better at producing the fuel. You could be making a type 1 error. Maybe it's really not better, but that's the best decision to make based on the data you have. Once again, I emphasize N1 and N2 happen to be the same here, 13, but they didn't have to be. All this stuff works even when N1 and N2 are different. The Smith-Satterthwaite formula still can be used with the calculator. You don't actually have to use the formula, just get the degrees of freedom from the calculator. And you can get to the conclusion still. As far as a confidence interval goes, we're not asked for one here. But we could compute one if we wanted to. Confidence interval for the difference. Let's go ahead and write down the numbers that we got with that 2-sample t-test. They were in there. So x1 bar was 15.523. X2 bar is 12.854. S1, I guess I'm going to compute the square root there anyway. I was thinking I was going to avoid it. It's about 2.427, say. I usually use more decimal places than this, but I'm trying to go quicker. It's good to keep a lot of decimal places and only round at the end, because if you round too soon, then your rounding errors build up, and that can make your final answer off by a certain amount. N1 and N2 are both 13. Yeah, I'm going to compute the square root still here, because the confidence interval formula is going to be x1 bar minus x2 bar plus or minus t alpha over 2 times the square root of s1 squared over n1 plus s2 squared over n2. All right, let's go ahead and take the time to compute that. Probably not keeping as many decimal places as I should. There's the thing under the square root, about 0.713533. Take the square root of that. This thing turns out to be approximately 0.8447. What is x1 bar minus x2 bar? 15.523 minus 12.854, 2.669. What t should I use? Well, it depends on what alpha is. Let's do the usual thing, 95% confidence interval. With degrees of freedom, df or gamma equal to 22. We need to look for t sub 0.05 with 22 degrees of freedom. I'll do it with tnv. Or inv t, excuse me. Oops, I made a mistake there. That should be divided by 2. So t sub 0.025. So I need an area of 0.975, 22 degrees of freedom. This is about 2.074. Plug that in there, multiply times 0.8447. The margin of error is about 1.75. So 2.669 plus or minus 1.752. Probably too many significant digits. Might be better to write 2.67 plus or minus 1.75. Anyway, we're 95% confident that the true difference of the two means is this interval, which if you wrote an interval notation, you would see it contains only positive numbers. And that would be strong evidence that mu1 is bigger than mu2. If you wanted to be precise about that, you'd say you'd reject it, the null hypothesis that they're equal in favor of a two-tailed alternative at the 5% level of significance because this doesn't contain 0. Let's do one more thing here just to confirm that concept in your minds. The p-value we got here was about 0.002 for this one-tailed test. So a two-tailed p-value would be approximately double that, 0.004. Or if I want to play it safe, let's go up to 0.005. What if alpha was 0.005? So that alpha over 2 is 0.0025. Still using 22 degrees of freedom, what would the t be in this case? Oops, forgot an extra 0 in there. 0.0025. Change this to 0.9975. We get about 3.1188. What I'm trying to get across here is if I use this for my t, for my confidence interval, and multiply it times the 0.8447 here, or was that a 9? Is that a 9 or a 4? I don't remember. Okay, let's do the S1 squared over N1 plus S2 squared over N2 again. Sorry about this. My other answer might be wrong if that's a 9 instead of a 4. Oh, it's a 4. Okay. If I multiply that by this 3.1188, it should be close to 2.67. Not quite. Oops, times 0.8447, is it? Wait, what happened there? What did I do? Oh, I did the wrong multiplication. 0.8447 times 3.1188. Is it close to 2.67, but a little smaller? Yes. Close enough for me to feel confident that this is confirming the conceptual point I'm trying to make, that if your confidence interval, whether it's this one or a different one, a bigger one with this t, for more confidence, 99.5% confidence, is going to reject the null when it contains only positive values. The null that they're equal in favor of a two-sided alternative rather than a one-sided alternative. Exactly when, again, that happened because we doubled the p-value. And I used a 0.005 instead of a 0.004. If I had used a 0.004, it probably would have been even closer to 2.67 here, the margin of error matching the value of the difference of the means. Is it clear what I'm saying? That's a lot of ideas. You can reject the null hypothesis in favor of a two-sided alternative in this context when the interval contains only positive numbers or negative numbers for that matter. When the alpha for your confidence interval matches the alpha that you're comparing the p-value to. It's a complicated thing, but we'll say. All right, we're going to go move on to chapter 11 now. Linear regression. Chapter 11 is a long chapter. We're not going to get through it. We're only going to do the first couple sections. And even in the second section, we're not going to do the entire second section. It's too much. If you page through it, you'll see the math gets kind of crazy. But we do it completely in applied stats. You have that to look forward to if you're taking applied stats in the spring. Today, what I want to focus on is just sort of what's behind the idea of the basic idea of linear regression. In particular, what is a least squares linear regression line? How is it used? But we're not really going to do what we've been doing recently with it today. We're not really going to really be doing confidence intervals and hypothesis testing today. We'll do that a little bit next week. Try to keep it as basic as we can. Okay. So here's the context. Connectors used in computers are subject to simultaneous multidimensional stresses such as high temperatures and mechanical stretches. So is that really the case? I don't know. It doesn't seem like it in real life. Maybe in industrial situations. A study is conducted to identify and quantify interface stresses. Experiments are conducted to investigate the relationship between pitch and connector length. Kind of a weird thing to study. So connector length is some sort of length of a connector in a computer. Between computers, I don't know, those are kind of small numbers. Here's another funny thing. We've got mixing metric with non-metric here. Those are in inches and the pitch is in millimeters. Pitch does refer to, like, you know, how much something is bending up or down. We've got two variables, an X variable and a Y variable. What are we interested, big picture wise, we're interested in, is there a relationship? And just glancing over the numbers, there does seem to be. As X gets smaller, the pitch, which you could call Y, is getting smaller. Or said another way, as X gets bigger, moving from right to left on the table, Y gets bigger. It seems like there is some sort of relationship going on. In the context of linear regression, we're wondering and maybe hoping whether it's a linear relationship. Do these points follow approximately a straight line or not? Analyze these data in the context of least squares linear regression. See page 428 for the full directions. I didn't, it's kind of long, I didn't want to type it all in. First thing to do is plot the data in what our book calls a scattergram, though I usually call it a scatter plot myself. Plot the data. Okay, I do have them in my calculator. Stat mode, edit. It's list 1 and list 2. So list 1, that's X, that's the connector length in inches. List 2, that's the pitch in millimeters. I did double check these numbers ahead of time. If you want to make a plot of these in a calculator, like this, see that's a thing that says stat plot. Maybe you've never used that before. Stat plot is what we want. So I need to use my second function button. Second, stat plot. And if you're going to use it with list 1 and list 2, option 1 will work. It looks like options 2 and 3 are also list 1 and list 2, but I need to turn it on. It's all these things are off right now. So I need to turn it on. And I believe the first type there is the default of a scattergram or scatter plot, list 1, list 2. Check the window. My numbers of X go from a low near 0 to a high near of 0.15. So maybe I'll use a 0.2 here. I'll make these 0.01 units apart. And the Y values go from close to 0 to close to 4. All right, let's see if it does it. I should probably check my regular Y equals screen to make sure there's no function in there. Okay, so if I hit graph now, there they are. Hey, yeah, you can just look at that and say that's pretty close to a straight line. Are these likely to be exactly in a straight line? No. Right? You got some data. It's going to be a very unlikely thing, if it's real life data, for them to be exactly on a straight line. especially if you're rounding or you're making continuous measurements or something like that, because of rounding and stuff, things are going to be off a little bit. But very close to a straight line. We can look at that and say there should be some line of best fit or trend line. All these words are used by different people. Line of best fit emphasizes a line looking about like this. That fits the data. Trend line, similar kind of thing, fits the trend. A line with a certain slope and a certain intercept. The intercept looks to be close to 0. You could try to eyeball the slope. In fact, since these data are so close to a straight line, you could probably just use 2 of the points to approximate the slope and do a rise over run. Like take the 3.81 minus 0.13 as a change in y, divided by 0.15 minus 0.005 as a change in x, a rise over run. 3.81 minus, what was it? 0.13. There's my rise from the lowest point to the highest point, and my run, 0.15 minus 0.005. So the slope looks to be approximately 25.4. Units of y per unit of x, so that would be millimeters per inch. Millimeters of pitch per inch of connector length. Weird units to use in combination. Approximately 25.4. So could we write that equation down? Could we just say y is approximately 25.4 times x? We could if we wanted to, and maybe I'll even plug that in here, 25.4 times x. Maybe I need more digits there, but let's use more, 25.379. 25.379 times x. Yeah, seems pretty good. You could go ahead and use that line. Is it truly the line of best fit? Is it truly the least squares regression line? Probably not. Is there a benefit to using this official least squares regression line, this official line of best fit? Yeah, there are benefits beyond just trying to fit the basic trend. Those benefits are statistical. The rest of, we can do inference ultimately when this is like a random sample from a larger population. The rest of chapter 11 justifies all that. So how do you find the true line of best fit? Well, with the technology, you can just have it do it for you. Stat, calculate, LinReg, linear regression. List 1 and list 2. List 1 is x. List 2 is y. Calculate. Slope's about 25.44. Intercept is close to 0. The official linear regression line for these data, sometimes people write it as y hat calculator uses A and B for the slope and the intercept. The book uses B1 and B0. B1x plus B0, where it's actually a little bit more traditional to put those in the opposite order in this context, B0 plus B1x. B0 is the intercept, B1 is the slope. It's a bit more traditional to write it in that order for some good reasons that I'm not going to get into. And here that's approximately, B0 is the negative 0.00316. The slope is the 25.4428, say. Oh, I'll go one more place there, 282x. Just kind of playing it safe with using more digits than I might need and just rounding at the end. If we graph this along with the other one, would we be able to tell a difference? Probably not at the scale that we were looking at here. They'll probably look like they're basically right on top of each other. For one thing, that other one looked like it was doing a good job. It's graphing it, and yeah, I'm not seeing a difference. That's one way to write the formula. Another way to write the formula is mu sub y given x hat equals b0 plus b1x is approximately the same thing. These different ways of writing the equation of this, I'll go ahead and call it sample regression line, because it is from a sample. Truly a random sample? Won't get into that. These two ways of writing it emphasize two different applications. This way of writing it, with a y hat on the left side, it emphasizes that you can use the regression equation to approximate an individual y value when you know x. This way of writing it emphasizes that that same quantity that is found with the same formula can be used to also emphasize the mean of the y values for that given x. If you looked at lots of computer connector parts measuring their lengths and their pitches, all for the same value of x, all for the same connector length, you could estimate the mean pitch in millimeters. You could also estimate an individual connector's pitch. So it's two different ways of thinking about using the regression line, and people use them for both things, to estimate an individual value y and to estimate the mean. You might think it's more valid, perhaps, to use it to estimate the mean, and that's especially true when your data are more spread out and not such a strong linear trend. Maybe more valid to use it to estimate the mean than individual values. If our data was not such a strong linear trend, but was more like a true scattergram where your points are kind of scattered all over the place, but maybe still with a linear trend, then using the regression line to predict an individual value of y for a given x seems a little bit more fishy, a little less likely to be valid, you might say, though people still do it. When I go back to that LinReg menu, compute it again here, there are other numbers in my calculator's version of this. R squared and R, what are those? Well, R is called the correlation coefficient. Hey, we talked about correlation a little bit back in chapter 5. Rho was the correlation back in chapter 5 for a bivariate random variable, a capital X and a capital Y. That's a theoretical correlation. This is a data-based correlation, and it's really close to 1. It's a strong linear trend with a positive slope is what that means. If it were close to -1, it would be a strong linear trend with a negative slope. If it's close to 0, it means it's not much of a strong linear trend either way when R is close to 0. But we definitely have a strong linear trend here. R is very close to 1. Your calculator may not give you those. And in fact, my calculator didn't give them to me when I first got this calculator. If your calculator doesn't, and you might have a calculator that doesn't give you R squared and R when you do LinReg, here's what to do to fix it. You can do this right now if you want. go to the catalog. Catalog button is down here above the number 0. Second catalog. Here's what it looks like for me. You want to go down to the D's, which you can scroll down to, or I think we can also just press the letter D. Up here. Oh, no, that didn't work. Did I do it wrong? Okay, I'm scrolling down. Go down to the D's and look for something that says diagnostic on. And then enter it until it says done. Done. Okay. If you do that, then your calculator should give you R squared and R. Why they don't set that as the default, I have no idea. It doesn't make any sense to me. Like, why wouldn't you set computing R and R squared as the default? Because it is of interest in doing regression. Can we compute the slope and intercept from a spreadsheet or from other formulas and not just use the what the technology gives us? Yeah, but the formulas are kind of complicated. Let's take our stretch break though first before we do that. All right, what we end up doing is we use a fairly complicated formula if we're forced to use a formula, and I do want you to get a little practice with this, if nothing else, to appreciate what your ancestors had to go through. And I'm one of your ancestors, mathematically speaking. I had to go through this 30-some years ago. The formulas are, well, for the slope is pretty complicated. And the intercept, once you know the slope, is not so complicated. They're on page 383. Right there. So B1 is the slope. Figure that out first. If you're going to use this formula, what do you have to do then? You're going to need to figure out the sum of the x values, sum of the y values, the sum of the products xi times yi, each one of those products, x1 times y1 plus x2 times y2 plus x3 times y3. It's really like a dot product, actually, two vectors. And if you look in chapter 12, they do bring linear algebra into play. We will use linear algebra in applied stats. You're also going to need this to add up the squared values of the x's as well there. And you need the sample size. Do I memorize this formula? You might think it's crazy, but I actually do, though I memorize it in a different form. And this form is worth writing down. Actually, I memorize it in two different forms. But let me tell you the main form that relates to what we see there. I memorize the formula for the slope as, well, symbolically it's written SS sub xy divided by SS sub xx. What does SS stand for? It stands for sum of squares. And the bottom of this fraction truly is a sum of squares. It's the summation. I goes from 1 to n of some squares. What are those squares? They are xi minus x bar squared. That really truly is a sum of squares, and so it makes sense to call it SS. Why XX? Well, it's kind of because there's two factors that involve x in this squaring. They're the same thing because you're squaring it. Xi minus x bar and xi minus x bar is kind of the intuition why there's two x's down here. The numerator, this SS in the numerator, is not technically a sum of squares, but for the sake of convenience, we call it SS anyway. It's a summation of a product. The first factor of the product is xi minus x bar, and the second factor is yi minus y bar. So that's not truly a sum of squares, but we call it SS anyway, just for convenience. And the first factor again involves x's, and the second involves y. That's why there's an x and a y there. I also then happen to memorize, partially just because I've taught this so much, that the bottom of this fraction can be written as the sum of the xi's squared minus the sum of the xi's quantity squared over n. And I also happen to remember that, once again, because I've taught it so much, that the top can be written as the sum, I goes from 1 to n, of xi times yi minus a fraction. So we got fractions within fractions here. Sum of the xi's times the sum of the yi's, all divided by n. And then if you multiply the top and the bottom of this fraction by n, which does not change the value of the big fraction because n over n is the same as 1, you will get the Book's formula. Okay? Why is this true? Why are these equal? That's not so clear. Is it hard to prove? It's not too hard, but it's easy to make a mistake. But where does this formula come from to begin with? We will talk about the derivation of this next Tuesday, but the derivation involves calculus, partial derivatives even, and setting those partial derivatives equal to 0 and writing a system of equations to solve for the unknown intercept b0 and the unknown slope b1. What in the world's going on here? Again, I'm not going to go through the details today. We'll save that for next Tuesday. But here's the big picture. Think of get this concept in your mind right here. Think of the xi's and yi's as being fixed numbers, given. This is somewhat analogous to what we did with maximum likelihood estimator, like on the exam even. The problem where you had to calculate that and you had data x1 through xn and you had the product and you did the log likelihood function and differentiated it. The xi's and the yi's are fixed numbers. What is the unknown here? The unknowns are b0 and b1. The intercept and slope are unknown. You are trying to figure out what values of b0 and b1 will minimize this quantity. So it's a calculus problem. It's a minimization problem. It's not an operations research problem. It's not a simplex method problem, right? Because This is not a linear function of B0 and B1, and there's also no simplex that you're trying to optimize it over. You're trying to find values of B0 and B1 that makes this quantity that is called SSE as small as possible. SSE stands for sum of squares of errors. These quantities that you're squaring are called errors. Notice you see EI squared. That's not the number E. EI represents this quantity, YI minus B0 plus minus B1 XI. What is that? Look at this picture. E1. These dots are the data points. E1 is this vertical distance here. Y1, the second coordinate of the first data point, minus the second coordinate of the point on this blue line, which is supposed to be the regression line. But what's the second coordinate of the point on this blue line? If you know the regression line's equation, you can figure it out by plugging x1 into the regression line. B0 plus B1x is the equation of the regression line. Oh, again, B0 and B1 are not known yet. If you replace x with xi, you will get the second coordinate, or if you replace it with x1, you'll get the second coordinate of this point on the blue line. That's not, there's no dot there, but just imagine there's a dot there. Y1 minus that thing, which is going to be what you get here when you replace xi with x1. You could also have B0 plus B1x in parentheses and subtract the whole thing. The fact that we have two minus signs here is because the minus sign got distributed through. That thing's squared, add those up for all the data points. And that is SSE, and that is the quantity you're trying to minimize. By taking partial derivatives with respect to B0 and B1, setting them equal to 0, and rearranging to get a system of equations. These are called the normal equations. In your second homework problem from this chapter, due next Tuesday, you're not going to use these formulas directly. You're going to write down the normal equations and solve them like in linear algebra. And if you haven't taken linear algebra, which might be the case for some of you because it's not a requirement for the course, it's not too hard to solve. You can look up a video about solving a system of linear equations, two equations and two unknowns. It's pretty straightforward. You can also, you don't even have to use elimination. You can use substitution. The numbers might be kind of messy, but it's definitely doable. We'll talk about this and with examples next time. Got a little over 10 minutes left here. Let's talk about finishing this problem. So we got a scatter plot, a scattergram with the calculator. And effectively that line you see is the least squares regression line. And why is it called least squares? Because we are minimizing a sum of squares. That's why it's called least squares. This is the only way to find a regression line? No, there are other ways. This is just the way that's most commonly used. Because it does, even though it's a complicated formula, it does result in a simpler formula than other methods. Oh, by the way, I forgot to mention, here's the intercept. Once you know B1, just compute y bar minus B1 times x bar. So you need to compute x bar and y bar as well. There is another formula that's not in the book for this. I will mention it here, and maybe we will confirm gives the same answer. You can also find B1 as by doing the correlation times the standard deviation of the y values divided by the standard deviation of the x values. It's not so clear why that works, but it does. Let's look at this in a spreadsheet. And then we'll finish the problem. Let's confirm some things with the spreadsheet. So I got the X values and the Y values here. Let's go ahead and compute the sum of the X's, for example, by doing this. Starting in A4, okay. Equals SUM. That'll be the sum of the X's. Copy and paste that to the next column. It'll be the sum of the Y's. There's 12 numbers. I could divide those by 12 to get X bar and Y bar. I also could use equals average. And that is, let's just double check that. That is this number divided by 12. Yep. It's the sum of the X's divided by 12, but doing it with equals average. Let's also get the standard deviations. Equals STDEV, never use the P. Just like in a calculator, you never use the sigma. Sometimes in problems you're given sigma, but you never use the calculator sigma. Here's the standard deviations. You can compute the correlation this way. Equals correl with 2 R's and 1 L. A4 through A15, comma B4 through B15. This might be worth writing down if it's something you've never done before. This is going to compute with the calculator called R. So it's like, it's close to 1. It's 0.99 something for this example. There it is. Let's compute the slope in a couple ways. Let's try it with the last formula here first. That'll be the quickest way. R times SY over SX. R is the correlation. SY divided by SX. What's this supposed to be close to? What was it? 25 something? This should be 25.44282 is what we got with the calculator. 25.4482, here we come. Yep. Let's also confirm it with this formula. Though I'll go ahead and use the book's form of it, where they multiply the top and the bottom by n first, canceling these n's and having n's in front of these things. But that does mean I need to compute these summations first. So I need more columns. I got the summation of the x's right there. I got the summation of the y's right there. I am also going to need the summation of the x squareds. I'll go ahead and make this heading like this. Take the A numbers and square them. Those are going to be really small. If I then copy and paste the summation formula to column C here, it will add those up. That's the sum of the x squared values, xi squared. I also need the sum of the x times y values. So I do this. A4 times B4 is what that says if you can't quite see in the back. Those are a bit bigger and their sum is going to be a bit bigger. And now I'm ready to use this formula again. I'll multiply the top and the bottom by n. So I need n times this summation, 12 times that, minus the product of those two, divided by 12 times this, minus this thing squared. And I should get the same slope. We're just trying to confirm we get the same answer to help you believe it, if nothing else here. So use parentheses, n is 12, right? N was 12. 12 times the sum of the xi's times yi's, that's this number, minus the sum of the x's times the sum of the y's, divided by 12 times the sum of the xi squareds. You're not squaring that thing. It is a sum of squares, but don't square it. But you do subtract the sum of the x's quantity squared there. So it's a matter of just being careful. This should be the same thing. Yay. The intercept, again, the formula in the book is y bar minus b1 times x bar. Mean of the y's minus the slope you just found times the mean of the x's. Y bar is there minus b1 times x bar. That'll be the intercept. This was a small negative number, negative 0.003 or something. Yep. What is the value of SSE when B1 is 25.4428 and B0 is negative 0.00316? I could figure that out. I think I won't for the sake of time today, but we'll do it on next Tuesday. Again, let's try to talk about finishing the problem. Now, it's a very long chapter. It's like you never get quite to the problem set as you page through it. So we did part A. We did part B. Estimate the regression line means find its approximate equation. Part C, calculate the residuals. Okay, maybe it will be good to do SSE quick. We've got 4 minutes. Calculate the residuals. What are the residuals? Those are the E's, which again don't represent the number E, they represent errors. EI, you could write, is YI minus YI hat, which you could also write as YI minus B0 minus B1 XI. Here's the spreadsheet. How? For each data point, first do YI, and then subtract, I'll use parentheses, the intercept, which is in cell B23, and use dollar signs if you want to keep it a fixed cell reference, plus the slope, which is in cell B22, times the corresponding value of X. That's EI for the first data point. And these numbers are all going to be pretty close to 0 here. Some negative, some positive. If you square them and add up those squares, that gives you SSE. And it's going to be pretty tiny here. That's SSE. But as far as the book's directions go, we did figure out the residuals. It does also say show apart from round off error, they round to 0 when you add them. And that's the case there. If I add that column E, that's very close to 0, except for round off error, that's in the ballpark of 10 to the negative 15. Next part, estimate the average pitch for all connectors of 0.03 inches. And part after that is estimate the pitch of a particular connector of length 0.03 inches. The answers to D and E are going to be the same. You use the regression line when X is 0.03 in both cases. For part D, where it's the average, you think of it this way with mu hat. For part E, that's the particular pitch of a particular connector, you think of it this way with y hat. But it's the same formula. You get the same answers. I won't take the time to do it. Part F, by how much would you expect the pitch to change if the connector length increased by 0.1 inches or by 0.05 inches? What's that about? Hint, think slope, rate of change. This is Calc 1 problem. If X increases by 0.1, you can even say this is a pre-calculus problem. How much does Y increase by? Along a line, if delta X is 0.1, what's delta Y? Change in X is 0.1, what's the change in Y? Uh-oh, nobody knows? What do you do along the line to find the change? How do you use the rate of change to find the change in Y when you know the change in X? Yeah, just multiply. 25.4 times 0.1. 2.54 millimeters would be your estimate for the change in the pitch. Or if delta X is 0.05, multiply that by 25.4. Part G, would it be reasonable to expect to be able to use the estimated regression line for pitches for lengths in this range, 0.175 inches through 1 inch? Those are all outside this data set. That's extrapolation. It seems reasonable if X is not too much bigger than this, but if X is up to 1 inch, that seems pretty far higher than these. And so I'd say it's getting a little bit unreasonable when X gets larger and larger. Okay, even though the trend was so strong. Things can go wrong if you extrapolate too far. All right, have a good day.
Share that spreadsheet.
Yeah, I will, thanks.